We're going to start our magnetism unit, and we're going to notice that there's a lot of things that magnetism and electricity have in common. So we're going to make a T-chart to compare and contrast magnetism and electricity. So on the left side, we'll write magnetism. And on the right side, electricity. Okay, and one thing we'll notice about magnetism is all magnets have two poles. They have a north and a south pole. In electricity, we don't have poles, but we have charges, and there are also two types of charges. We have a positive and a negative. Another thing that we notice about them, magnets can attract or repel. So we're going to say like poles repel and opposites attract. And that's going to be the same for electricity. We know that like charges repel and opposites attract. Now, we also talk about electric fields. And we learned that electric fields point from north to south, or sorry, from positive to negative. We also have magnetic fields. And they point from north to south. And they're going to look very, very similar. I could draw a positive and a negative here. And if you remember, the way the electric field looks like for that, they come out of the north and curl around and bend into the south. And it's the same thing for, say, a bar magnet. It has a north end and a south end, and the magnetic field lines are going to come out of the north and point into the south. So they look very, very similar to electric fields. And then something that's also true, we can tell where the electric field was strongest because it was strongest where the lines are closest together. It's going to be the same rule, okay? The field is strongest where the lines are closest together. And that's going to be true for both electricity and magnetism. Just as an aside, this is one thing that's kind of interesting. All magnets seem to have two poles, a north and a south. In electricity, you can have a positive charge by itself or a negative charge by itself. In magnetism, you never see a north by itself or a south by itself. That would be called a magnetic monopole. And for some reason, those don't seem to exist. In theory, they should, but every magnet we've ever looked at always has a north and south pole. So that's one of the kind of unanswered questions of physics, is why can't magnetic poles exist alone if charges can exist alone? Now, magnetic field strength, remember it's going to be strongest where lines are closest. And they actually use that to define the strength of the magnetic field. The letter for magnetic field is B. You couldn't use M because M was mass, so they picked B. And B is going to equal the number of lines per square meter. Now sometimes they'll call a number of lines Webers. And a Weber per meter squared is equal to a Tesla. So the unit for magnetic field strength can be Weber per meter squared, lines per meter squared, or Tesla. They all mean the same thing. Now there's one thing that we're going to have to pay attention to. When we're doing magnetic fields, we actually have to think in 3 dimensions. Okay, if I want to draw a magnetic field pointing to the right, I would just draw an arrow pointing to the right. If I want to draw a magnetic field pointing down, I would draw an arrow pointing down. But if I want to draw a magnetic field going away from you into the page, how would I draw that? So they've come up with a convention. And think of an arrow. If you actually had a physical arrow made out of wood, okay, and you were shooting it from a bow, if it was going away from you, okay, you would see the feathers, okay, which maybe would make something like an X. So this is the symbol meaning into the page. And if the arrow is coming out of the page towards you, you would just see the tip. So that's a dot. So you would see the tip of the arrow, which is a dot, and a dot stands for out of the page toward you. So here we have a magnetic field. The X's mean it's pointing into the page, and there are a bunch of magnetic field lines, and we have an area. So we're going to find the strength of the magnetic field. It's going to be B equals lines per meter squared. So I would just count the lines. So there's 1, 2, 3, 4, 5, 6 lines across, and 1, 2, 3, 4, 5 lines down. So that will give me 30. So we have 30. We can use Webers for our unit. And our area for this is meter squared is going to be 2 meters by 6 meters, which is going to, by 3 meters, which is going to give me 6 meters squared. So it's 30 Webers over 6 meters squared. That's going to be 5, and I could write Webers per meter squared, or I could write a capital T for Tesla. So the strength of the magnetic field is 5 Tesla. Now we all know there are some naturally magnetic materials. Okay, some examples are iron, and to a lesser extent, cobalt, and nickel. That are naturally attracted to magnets. Not every metal is. Aluminum, gold, silver, they're not attracted to magnets, but iron, cobalt, and nickel are. Again, a little aside, nickels, okay, like a 5-cent piece, used to be made out of nickel, and they would have been attracted to a magnet. Nickel became kind of expensive, so we stopped making nickels out of nickel. However, in Canada, they still use nickel in their coins. So Canadian coins are actually attracted to magnets. Now the question is why? And it's a thing called the domains theory. The idea is that iron is made up of tiny magnets called domains. And normally, the domains point every which way. And normally the domains aren't aligned, so they're pointing every which direction. I'm drawing these, so this domain is a tiny little magnet. It has a north end and a south end. So they're pointing every which way in a regular piece of iron. They're not lined up. So we'll label that this is unmagnetized iron. But then, if we put it near a magnet, so here's a permanent magnet, it's a north end, and then we take our piece of metal, what's going to happen to all those little tiny domains is that they are going to line up so that their south ends are aligned or pointing towards that north, because the south end is going to be attracted to the north end of the permanent magnet. And it's going to look like this. And now this iron is magnetized, and it has a south end and a north end. So at least temporarily, this piece of iron is actually a magnet. So where all the south ends are pointing, we're going to label that south end of this magnet, and this is the north end. And then this piece of iron will be attracted to the permanent magnet. So in order to make a magnet, we have to get the domains to align and kind of stay that way. And usually it won't, because just the normal motions of the atoms due to the heat will cause these to scramble themselves again. As soon as I take this thing away, this permanent magnet away, these will scramble themselves again pretty quickly. If I want to get them to stay the same way, I can leave them in a very, very strong magnetic field for a long time, and then they'll get pretty well aligned. Or I can rub a magnet in the same direction over it repeatedly, and that'll make the magnet a little bit more permanent. If I want to get rid of magnetism, I have to get these to scramble. And there's a couple ways to do it. One is just to kind of pound on it like with a hammer, and then they'll scramble. The other way is actually heat it up, because if I heat it up, the heat is going to make the molecules move faster and they'll scramble more quickly.